All right, let's look at section 11.7. Let's discuss the strategy for testing series. The idea here is in this assignment, we're going to see all of our series tests together. So whether it's test for divergence or geometric series test, maybe we encounter a telescoping series and assess via definition, or whether we're using the integral test or comparison test or the ratio test or the root test or the alternating series test, p-test even. We're going to use any of them as needed. So let's take it bite by bite. Determine whether or not this series is convergent. This one here, it looks like it's a video example. We're ultimately going to make a comparison here, a limit comparison with 1 over n squared. And so, or I guess maybe even a direct comparison with 1 over n squared, because the idea here is that cosine n can only get so big. And is at most 1 when you look at absolute value. And so the sum of the absolute values of the terms of this series must converge, which means the sum of the terms in the series must converge. If any series is absolutely convergent, no matter the sign on any term, you get a convergent series as a result. What about this one? First glance here, these terms, not the sum of the terms, but the terms themselves, limit to 1/5. In fact, that's what's suggested of you. And since the terms themselves limit to 1/5 and 1/5 is not 0, the sum of the terms eventually will start looking like plus about a fifth, plus about a fifth, plus about a fifth. And do that perpetually, you will get a sum that diverges to plus infinity. What about this next one? Oh, hey, the -1 to the end. That's an indication that we are dealing with an alternating series. And when you look at the terms of this series, indeed, they are heading to 0 because we are denominator heavy, and they are decreasing to 0 precisely for that same reason. The fact that the denominator has more power than the numerator, the denominator will grow faster than the numerator, and the terms will decrease to 0. And that is the precise criteria for the alternating series test. So there we go. What about this next one? Okay, looking at this, okay, as n gets large, that's going to tell us what happens with the series. And as n gets large, upstairs, we essentially have a n cubed square rooted, which is like n to the 3x. And what about downstairs? Downstairs, we've got like 7n cubed as n gets large. The other terms are going to be inconsequential. And so if you look at the highest degree terms, we're setting up for a limit comparison test here. So simplifying this out, what we have 1.5 extra powers of n in the denominator with a 7. So if we do a limit comparison test with 1 over 7 to the 7n to the 1.5, we would have an appropriate limit comparison to deal with here. So nothing too wild or crazy there. Ooh, looking at this one. How are we going to deal with this? Boy, that when I see an exponential in a series, I'm either thinking to go with a ratio test or something like that, or I'm thinking geometric series, or I'm thinking integral test. And in fact, the integral would work really nicely here because this bit that's inside our exponential function could be our u, and then du would take care of the x squared. So yeah, integral test is going to work really nicely. And note, the terms of this, if you take that e to the negative power and put it downstairs, the e is going to grow way faster than the n squared. And so you'll have a decreasing terms. They will be positive because n squared will be positive, the exponential function always positive. And yeah, you're going to have something continuous because you're dividing two functions that are continuous. So you would have all three criteria for the integral test. And what a nice thing to be able to use an integral to assess the convergence of a series. This one, if we just had 1 over 3 to the n, we'd have a geometric series with common ratio 1/3. However, we've got this extra 4, but that extra 4 is actually shrinking the value of each of our terms. And since we know a geometric series with common ratio 1/3 converges, because 1/3 is less than 1 in absolute value, then we would subsequently know that this series converges as well. What about this one? Hey, there's a telltale sign of which test to use here, and it's the factorial. In fact, exponential expressions sort of make me lean ratio test as well, but definitely factorials are like a tell for ratio test should work out pretty well. And yeah, in fact, the ratio test will work well. I believe the ratio test will give you a limit of 0 here, which means this series essentially acts like a geometric series with common ratio 0. Boy, that's going to converge in a hurry. In fact, that k factorial just gets so big so quick. Yeah, okay, well, anyways, moving on. Hey, alternating series here. We've got -1 to the n, so we've got an alternating series. Do the expression for the terms without the -1 over n decrease to 0? They definitely go to 0 because the n grows faster than the ln n. You could run a L'Hopital limit as n goes to infinity to verify this. And in fact, because then the denominator is growing faster than the numerator, you will get decreasing behavior, because when the denominator grows faster than the numerator, the fractions will be decreasing. And so we would converge via the alternating series test. But now the question is, what kind of convergence do we have? Is it conditional or absolute? And if you look at the series expressions, if you neglect the -1 to the n, the terms of this series are bigger than those of the harmonic series. The harmonic series, sum 1 over n, we know diverges, and throw an ln n upstairs. Now the numerator just got bigger. And bigger numerators in a fraction over n would mean the sum of those terms would grow even faster. The partial sums of those terms would grow even faster than those of 1 over n. And so ln n over n grows faster than 1 over n. 1 over n already has a sequence of partial sum that's unbounded. So the ln n over n has to be unbounded as well, which then indicates conditional convergence in this case. What about this next one? Hey, this is tailor-made for the root test, because we've got that power of n. So when you run the root test, you will either get absolute convergence or divergence. I mean, there's a possibility you'll get the inconclusive case if the limit is 1, but in this case, whenever you take the root, the nth root of this expression, you'll just get 5n over ln n, and in fact, that will limit to infinity. And so, yeah, you will end up, I think, with divergence in this case, but run the root test, doubly verify. Here, this is curious, but check it out. Arctan is always just between -pi/2 and pi/2. If like, ask Desmos to graph yourself here. Let me just plug it in. Ask Desmos to graph yourself the arctan function. Let's see, let's just do tan inverse of x. And you can see never less than -2, never greater than 2. In fact, there's an asymptotic pi/2 and -pi/2. And so when I think about the contribution of the arctan, it's almost negligible compared to the n to the sixth. So the n to the sixth is going to grow way faster than the arctan. The arctan only gets at most to pi/2, but boy, n to the sixth is unbounded. And as a result, the terms of this series are going to be decreasing in absolute value and approaching 0. So by the alternating series test, we got a -1 to the n, we would converge. But what type of convergence do we get? Well, what could we do here? Maybe we run a comparison test. We could run a comparison test, a limit comparison test with just 1 over n to the sixth, and the arctan would be meaningless. And yeah, at the end of the day, I think as n goes to infinity there, you'd end up with a real number for your limit, and I believe you end up with absolute convergence here. That n to the sixth, it's feeling like a p series with p equals 6, and the fact that 6 is bigger than 1, I'm leaning towards convergence here. So doubly verify that for yourself. Classic, true, false. This is intuition about series 101. If the terms go to 0, must the series be convergent? Not so fast. Think about the harmonic series, right? Now, if we know the terms don't go to 0, the test for divergence tells us we must be divergent. And while it is true that every convergent series has terms that go to 0, it is also true that simply knowing that the terms go to 0 is not enough to guarantee convergence, because the harmonic series would be an example of a series whose terms get small, but whose sum of those terms grows without bound, and as a result, we get divergence of the series. So the fact that you have infinitely many numbers that you're adding up gives this curious behavior, and wow, this is a classic. Not the first time we've seen that, if I'm not mistaken. How to test the divergence or convergence of this? I just see polynomial over polynomial. I want to compare this to 1 over n and use a limit comparison test. The limit comparison test should give you a favorable result there. Do the math, compute the limit as n goes to infinity of an over bn, where your bn is 1 over n. You should end up with a limit between 0 and infinity, which would give you a conclusive result to say that this series essentially functions like 1 over n. And of course it does, right? Because as n gets large, you're essentially producing terms of approximately magnitude 1 over n. And so this series should act like 1 over n. In fact, it does. What about here? Here we've got an alternating series. Now, the denominator is of higher degree, so the denominator will grow faster than the numerator, and the terms will decrease to zero. There's no denying this. But because we are an alternating series, all we're asking for is convergence or divergence. If we were asking for conditional convergence, this is actually going to be conditionally convergent. I wish they asked that, because if we just took away the -1 to the n, the 1 over n does diverge. But with the -1 to the n here, hey, we're alternating, and the alternating series tend to converge more easily, which is why we only have to look at the terms without the -1 to the n and say, do they decrease to zero? They do here, convergence results. Looking at this one, so I see an exponential in here, which makes me think ratio test. And in fact, unlike the previous example where we had an exponential, where it was some convoluted expression that almost seemed U sub friendly, here I kind of just want to use the ratio test. E is just some number between 2 and 3, 2.7-ish. And if you run the ratio test here, I think you should get a conclusive result. So yeah, try that out, see what you end up getting. I think you'll get the ratio test evaluating to a limit of E. I could be wrong, but yeah, double check the computation. What about this next one? Hey, we got an alternating series. And the question is, with an alternating series, do the terms decrease to zero? And while upstairs, we are taking pi times itself 6 to the n times, which is a lot of pi's being multiplied. Pi is just a number. It's like about 3, right? So we have a number a little bit more than 3 being multiplied by itself many, many times. But downstairs we have a factorial, and it is true that factorials will dominate exponentials, and as a result, the denominator of this expression will grow faster than the numerator eventually, and that will cause the terms to decrease to zero, which is what the alternating series test demands for convergence. What about this next one? I kind of want to split this, right? Because the 1 over n squares, that's just a p series, that will converge. And the 1 over 2 to the n, that's a geometric series with a common ratio 1/2. So since each of these converge individually, we could then distribute the summation and get whatever the first one adds up to, plus whatever the second one adds up to. I think the 1 over n squareds add to what, pi squared over 6, and the 1 over 2 to the n's add up to 1, but it doesn't matter what they add up to, we get convergence regardless. Again, an alternating series. Boy, you've had a lot of alternating series. And look at the terms without the -1. Do they decrease to zero? And the answer is definitely yes, right? Because as n grows, the denominator grows, and as n grows, the denominator grows without bound, which says the fractional expression is going to be decreasing as n grows, and in fact decreasing to zero. So that's convergence by the alternating series test, and that's a wrap on the robust section 11.7 strategy for testing series exercise set.